already before in different contexts, and you have a deep dive in there. So very excited to have you here today.
Great. Thanks for having me. Hello, everyone. So multimodal AI. Now, multimodal AI's goal is to really understand this whole multisensory world around us. We have seen already great progress in systems that are able to understand our spoken language or the text that we type into our computers. But these systems don't also understand our voice, our vocal expressions, and any facial expressions or body language when conveying our thoughts. Similarly, we've seen great progress in AI for health. We have progressively better AI systems, computer vision systems that are able to understand X-ray images. But as we all know, a big part of a doctor's job is to do holistic assessments of a patient's health and well-being. That involves, digging deeper, putting cells under the microscope and interpreting those cells, putting people in the ICU and measuring sensor information from these ICU sensors. And this is the tip of the iceberg. We've seen great work in developing more and more commercial wearable sensors to track our health and wellness, mobile data that can track our daily mental emotional states, and of course, an increasingly larger and larger collection of real-world data modalities that are especially important for science and engineering. So the whole goal of multimodal AI is to be able to build AI systems that can learn representations and features, and more importantly, combine these different indicators to bring about deeper understanding of the world around us. To give a glimpse of several applications, I've already mentioned health quite a bit. A lot of the work in our group applies multimodal methods to try to holistically understand a person's health and well-being. And that can include indicators of physical health, such as systems that you can put in the ICU to monitor how patients are developing, whether they're in emergency and they need help from doctors and nurses. It includes systems for understanding a person's emotional well-being, so understanding a person's mood and whether they might be depressed or stressed, or do children show early signs of autism? Very important biological and medical questions. And of course, also understanding the wellness of people in groups. How are people interacting with each other? Are they flourishing? Are they happy in social interactions? Another big key application of multimodal AI is understanding the physical world around us. When we're trying to look at climate data or environmental data, it's often a mix of sensors, mix of imaging, both natural RGB imaging, thermal imaging, tactile data, and more. So this just give a glimpse of some of the work in our group. We do a lot of work in combining vision and touch, two very key properties for us to understand the world. And of course, it'd be great if we could endow robots with also the senses of vision and touch. So over here, we have robot arms that can see. And that's great because you can push these robot arms and they can rely on computer vision and their cameras to solve the task. And they can also feel. So you can start occluding these cameras and these robot arms can still feel around the object to complete the task. Recently, we've also begun to dive into the sense of smell. Key property of us people, we use the sense of smell all the time to understand our environments and what we're eating and interacting with. Can we endow AI systems with a sense of smell as well? So right here, I'm showing an example where this blue chip over here is a gas sensing chip that picks up different volatile gases released by different foods and beverages. And by collecting data and programming this AI chip, it can recognize different substances just based on the gases and smells that they emit. So you can bring this chip to a candy bar, to a jar of peanut butter, and it can detect the presence of peanuts from smell alone without looking at a substance. And of course, that can be very useful for people who might be allergic to peanuts and they might want to put this sensor on things before they start eating them. So lots and lots of multimodal data in the physical world. In generative AI, of course, we've gone beyond language to language systems to any modality systems. Systems that can take in text and generate a video of it, that can take in a still image and generating the next couple of frames to make it a video. It takes in a video and finds the right audio and music for the right video clip. And of course, a lot of this is for fun. It's to help artists and creative professionals, but it's also a big trend of using generative models for different modalities to generate more synthetic data that can be used to further train your models. So you've seen work in generative models of images to train better image models, generative models of sensors to train better sensor models. And a final application that is also key in today's multimodal AI is what we call multimodal agents. These are systems that go beyond making a prediction. So whether a person is healthy or not healthy, what is the smell of the substance, beyond making a prediction to systems that can actually take actions for you, taking actions over multiple sequential steps. So I'm sure all of you have seen examples of these digital agents on a computer that can understand the natural language instructions that you type to it, that can understand visual information and HTML data on these websites and execute these instructions to solve the task, in this case of doing online shopping. And of course, this used for online shopping, travel bookings, helping you be more productive. But these agents are going to be used in many, many more applications. They're going to be able to understand lots of forms of multimodal content, like HTML and different operating systems, understand different databases, and of course, also be used for various forms of scientific discovery to iterate through different research articles, grounded in different experiments, and perhaps even one day conduct those experiments autonomously. So lots of applications of multimodal AI. And in today's talk, we will cover the key principles, the key advances in this field through 3 parts. So in the first part, we will discuss what is multimodal AI. We will cover the nature of multimodal problems, what different modalities are, and the key characteristics of what makes a problem multimodal in nature. We will then cover in part 2, why is multimodal AI difficult? What are the specific challenges in multimodal AI that are not typically seen in single modality, language only, and vision only problems? And finally, in part 3, we will cover latest advances of what is next, the next generation of methods in multimodal AI so that you can learn about them early and start applying them to your problems early on. So to start, we have taught multiple courses, written survey papers, and given tutorials on this topic. If you are interested in the longer semester-long or multiple hours-long version of this talk, please check out these resources. So to start, before discussing multimodal AI, we have to first discuss what is a data modality. And you can think of a data modality as a way in which some physical phenomena is expressed or perceived in the world. When you think of these data modalities, you often have some sensor, which is a computational model that is collecting data from the world and digitizing that on a computer. Given these sensors, you can think of a spectrum of raw modalities, which is data collected more closely to the sensor. For example, the raw speech signal that this microphone is picking up, or a raw image that's being captured by a camera. These are examples of more raw modalities. And on the other side of the spectrum, more abstract modalities, data modalities that go through more pre-processing after being collected in its raw forms. So from speech signals, you can extract language, the words that I say. From images, you can detect objects, and you can further detect sentiment. So whether you like this lecture and not like it, what the object category is from the detected objects. So these are ways of making these data modalities more abstract and extracting features from it. So multimodal, therefore, refers to problems that involve multiple data modalities. And when different data modalities are involved, there's 3 key challenges. The first key challenge is that of heterogeneity, the fact that data modalities collected from different sources are often very different, and these differences causes it to be very difficult to process them together in the same model. A second key challenge is that of interconnectedness, and we break that down into both connections and interactions. Connections describe the fact that data modalities often are connected and share some overlap in information. Interactions describe the phenomena that when you bring these data modalities together, they interact and fuse in some way to bring about new information. So I'll cover these again in more detail. The first key problem in multimodal learning is the fact that data modalities are heterogeneous. And you can roughly think about this as the fact that you have different modalities, they show different information, they show different qualities, structures, and representations within these data modalities. And again, you want to think about heterogeneity as a spectrum. So a spectrum from cases which are more homogeneous, which are more similar, and to more heterogeneous with more and more different qualities. So images on 2 different cameras. That is still a multimodal problem, but a problem which is more homogeneous in nature because they're both imaging problems of the same phenomenon, although they might have different differences due to different camera angles. Text from 2 different languages. Now you're starting to see more heterogeneity because sometimes different languages can have very different grammars and vocabularies and syntax, but for the most part, they can still be translated one from the other. Language and vision now becomes even more different because these are fundamentally different ways. One is a language and sequential modality, one is a visual and spatial modality. And finally, you can have something much more heterogeneous like language and sensory information. There might not even be a one-to-one mapping. There might not be a language that describes these sensors, and therefore they're much more heterogeneous. So that's the first key challenge, the fact that modalities are heterogeneous. The second key challenge is that modalities often show some connections, and we define connections as some shared information that relates these modalities. Again, you want to think about this as a spectrum with parts of modalities that are stronger and therefore more shared information, and to settings which these modalities are unconnected with no shared information at all and with almost exactly unique information in one as compared to the other. So again, given some example like this, image and a caption, you can think about some parts of these modalities that are connected, right? They both refer to a teacup, referencing the laptop, but there's also lots of information in the image that is not in the caption. For example, the color of the sofa, the presence of the table, and the size of the table. All this information is unique to the image, but not present in the language caption. And finally, the third key challenge, the third key principle in multimodal AI is the fact that these modalities often interact in some way to combine and provide new information for a task. So again, following on these Venn diagrams of modalities with some shared information and some unique information, interactions arise when you're trying to predict some task Y, given these two data modalities. And there's several key types of interactions, one of which is redundancy, the fact that these two modalities provide the same information, and you're trying to exploit the same information to predict this task. So one example could be someone saying, this movie is great, with a huge smile on their face. Right? Obviously, both of these are very positive, and together you're very confident that the person really, really enjoyed the movie. That's an example of redundancy. Redundancy is in opposition to uniqueness. Uniqueness refers to the fact that one of the modalities has the right information and is unique to that modality, not present in the other. So most of the times we might say something like the movie does a good job developing slightly positive with neutral facial expressions, not really expressing yourself in your face. And out of these, it is the unique information in language that has to be picked up by the model to make that prediction. And finally, the third and perhaps coolest interaction is that of synergy, where there's some emerging information that only arises when you bring these data modalities together. So you can think of a scenario where you might say a word like wow, which is very positive, but with anger and frustration on your face, which is negative. And that actually indicates the person is actually being sarcastic about the topic. And that's an example of synergy because it requires you to combine and compare both of these outcomes and look at their differences before realizing that a person is actually being sarcastic. So to summarize, what is multimodal? It defines problems which have several key principles, which makes them very unique and very difficult to tackle. Essentially problems that involve multiple data modalities, which it brings about multiple sources of heterogeneity, the fact that data modalities are often very different, and these differences makes it very difficult to process them together. The idea that modalities show some connections, so that's overlap in information that is shared between them, and the fact that they interact. When there is some task Y they are trying to predict from both of them, the information combines and interacts in different ways to predict that task. So multimodal is the scientific study of heterogeneous and interconnected data. So now, why is multimodal hard? So multimodal AI, because of these three key principles, the heterogeneity, the connections between modalities, and the different ways in which data modalities interact, often introduces several key challenges, which inspires people to build different types of multimodal models to tackle these challenges. So to illustrate these multimodal models and the challenges that they tackle, I'm going to use this general schematic to represent data modalities. So A in different red triangles in a sequence, B in blue circles, and C in green squares. And again, you've noticed that I drew them in this sequence because most real-world data modalities do come in some sequence, right? You might be saying multiple words, you might be showing different facial expressions, you might be collecting sensor readings across different periods of time, and so on. And of course, multimodal AI is all about bringing in all these forms of data in their elements and their sequences through some computational model to learn representations and to make predictions. So all of these challenges really go into designing what that orange box of multimodal AI looks like. So I'm going to cover 6 key challenges. These are 6 key challenges that really define the field and make it unique. And whenever you're faced with some multimodal problem in your practice, most of the times you're going to be defining it into one of these 6 challenges, looking at what the recent work is in that challenge and building upon the recent work in that challenge. So it's a good way of taxonomizing this pretty broad field. So the first challenge is what we call representation. How do you learn representations that capture the interactions between individual elements across data modalities? So let's unpack that real quick. As we saw, we're looking at data modalities which have multiple elements in some sequence. So words that you might be saying, sensor readings across some sensor that you're collecting, images across the entire video. For the purpose of this first challenge on representation, we're going to simplify the problem by just looking at individual elements. Right? We're going to take care about the other elements and the sequential nature of the problem later. So just focus on individual elements. And then the problem representation is really how do you represent these individual elements and also model the joint representation between them, the fact that they interact in some way, that they're related in some way. Now, of course, this is a core building block for almost all multimodal problems. You have to define how you represent these elements and how you represent these elements together with each other. So there's 3 ways of generally doing that, 3 ways of learning these representations. The first way is what we call fusion. So in fusion, the goal is to take in 2 elements and learn one joint representation that best fuses them together. This is super useful when these data modalities show some synergy, and therefore fusion discovers the synergy between them. Fusion is in contrast to coordination. In coordination, your goal is to learn separate data representations. So in this case, 1 for each data modality. So that's 2 representations. But instead of learning these 2 representations independently, you want to coordinate them using some similarity function. So this might be a similarity function like contrastive loss, like some cosine similarity, and so on. And this is super useful, especially because now you can take in 1 data modality, learn the representation, and retrieve something that is close together in that space and generate the other one. So coordination enables you to do retrieval, whereas fusion will not enable you to do something like retrieval. The downside, of course, is that coordination doesn't really combine information in a way that exploits the fact that new information could synergize. And finally, the third type of representation is fission. So that's kind of a setting where you learn more representations than the data modalities that you started with. So you have 2 data modalities, you might learn 3 representations, some which capture the joint information that's overlapping between them, and some that capture the unique information in one and the other. So lots of ways in also learning disentangled and fission representations. So challenge 2 is alignment. So as we said, in representation, we only captured 1 element in each data modality. We said we leave the other elements for the other challenges. So that's exactly what we're trying to do in alignment, dealing with the fact that most data modalities have some internal structure with multiple elements. How do we capture the connections between all of these data elements in one and the other? So of course, most of these elements follow some structure. This structure could be spatial in the examples of images, and it could be hierarchical in the case of graphs or other data forms. So 3 challenges in alignment. Again, one challenge is this idea of discrete alignment. In a setting where your data modalities are discrete and nicely chunked into boundaries, so words that I'm saying are nicely chunked into individual words, facial expressions that I'm making are nicely chunked into individual facial expressions. How do you define the linking between each of the words with each of the facial expressions that I'm using? This is called explicit alignment. Sometimes people also use the word grounding to refer to this problem. Grounding words that you're saying with something in the visual modality or some other modality. Discrete alignment is made more challenging in the case when data modalities are continuous. So there is no clear segmentation into discrete boundaries. So in this case, you have to first take continuous data, like sensors, and actually learn this discretization or learn this segmentation before you can do alignment. And of course, you have to figure out what the granularity of individual elements are. So whereas in this first two, alignment is the main goal. Your goal is to link one element with the other. In this third sub-challenge, this alignment is only used implicitly to learn better representations. So we call this challenge aligned representations. So classic transformers is a classic example of this, where transformers allow you to learn the relationships between one word and other words in the sequence, as we have seen, but it's not important to exactly learn these relationships. What's important is to use these relationships to contextualize your representations into one that you can use for downstream tasks, like next word prediction or classification. And we'll cover more extensions of transformers in the rest of this talk. So first two challenges on just explicitly learning the alignment, third key challenge on implicitly learning the alignment to learn better representations. Challenge 3 is reasoning. So we've talked about representing individual elements. We've looked at aligning different elements across time. In reasoning, the whole goal is to combine all this information, usually through multiple steps, to exploit the problem structure and to make some prediction. And of course, when we think about combining things over multiple steps, it used to be the fact that we would do this over multiple layers of neural networks to learn more and more abstract representations that are more semantically meaningful and are more predictive of the task. But nowadays, we have more and more powerful systems, especially LLMs, that allow us to explicitly do this reasoning. So this reasoning can be parameterized by the structure, whether it's a linear chain, whether it's a tree-based or graph-based reasoning structure that defines the way that you should be combining information. And another key parameter is what are the intermediate steps in the reasoning. Nowadays, we've seen that language can actually be a very useful step of reasoning because now LLMs can generate explanations of why they made a prediction in addition to the prediction itself. So challenge 3 on reasoning tackles these challenges. And of course, you always need to have some external knowledge and some domain knowledge to inform the reasoning process and its evaluation. Challenge 4 is generation. So most of the things we've talked about were mostly about predictive models. Now in generation, especially multimodal generation, how do you learn a generative process that exploits the nature of different multimodal problems and reflects the interactions between them? Again, 3 sub-challenges. One is about summarizing data. If you have lots of multimodal data, which is really high dimensional and large, how do you summarize it into the most important features? Translation is about taking data in one data modality and translating it into equivalent content in something else. So taking a caption and generating an exact image of it. That's translation. And finally, creation. How do you go from something smaller to something larger while still maintaining some semantic coherence? So for example, starting with an image and generating an entire video with audio and text that is all synchronized with each other. Challenge 5 is what we call transference. In many settings, we have a problem where you have some data modality that you care about, modality A. This could be something like medical images or scientific data, chemical data. And it's of real world practical importance, but you don't have that much data. Whereas there's some other data modality B that is really large and rich in data. So this could be internet text or internet scale images and so on. Transference studies this problem of how you transfer information between modalities, usually from something that is high resource to something that is low resource in a setting that you actually care about. So we call that transference. Several sub-challenges here. One is transfer learning across data modalities. Surprisingly, this works. You can train general purpose models, even things like large language models. They transfer really well to computer vision tasks, to robotics tasks, as people might have seen. Another key way of doing this is through co-learning. There's ways of introducing external auxiliary information during training, and either as the input or as a prediction target, and throwing these away during testing, so that during testing, you're still only using the limited data that you care about. And finally, ways of inducing behaviors across different models, especially if your models are things like black box APIs. And last but not least, the 6th challenge is what we call quantification. In this setting, what the first 5 were more about building models. The 6th challenge is about understanding. How do you do deeper empirical and theoretical analysis to make sure that these models are actually operating the way that we want them to operate? So that involves deeper understandings of when and why data is different and what that does to the learning process, how different data modalities interact, and the most appropriate models to capture those interactions, and also explaining phenomena like why is multimodal data that much harder to learn from, especially during optimization when one data modality might overfit and the other one is still barely learning. So to summarize, whenever you're faced with a multimodal problem, you always want to zoom into one of these challenges that you're tackling. And usually it's maybe one, at most two of these challenges. Two of them are extremely common and are faced in almost all problems. You have to face the challenge of how to represent your data, represent the individual elements and represent how they combine, whether that's a joint representation, infusing them, whether that's two coordinated representations or multiple representations. You have to also deal with the alignment of multiple elements in your sequence. So how does one word align with different parts of the image, or how do parts of sensors align with other parts of other sensors? And these are almost universally present in any multimodal problem. After that, typically you have to deal with how the model reasons, how the model combines information from what you've extracted from the representations and align with other data modalities. And again, this reasoning process can be using fully black box neural networks, but nowadays it's also a big opportunity of making this reasoning process more transparent using language. That's used to make a prediction, but beyond making a prediction, there's also settings where you're trying to generate more data, either by translating from one to the other, summarizing, or even creating more data. There's also a challenge of transference. So instead of just making a prediction on one problem, you're trying to transfer higher resource to low resource problems. And finally, quantification is this magnifying glass that aims to revisit each of these challenges and aims to provide a deeper empirical and theoretical understanding of what works and what doesn't. So again, all these slides are available. Our survey paper really covers each of these 6 multimodal challenges in detail, the sub-challenges in detail, the latest work in each space, and that can be a starting platform to discover what's the next works that should be worked on. All right, so to summarize what you've seen so far, what is multimodal? Multimodal has 3 key principles. It is a scientific study of heterogeneous, so very different, connected, sharing information, and interacting data, where there's some new information to be discovered when you fuse these data modalities. Why is multimodal difficult? We covered 6 key challenges at a high level. How do you represent elements? How do you align multiple elements that are often seen in some sequence? How do you do this reasoning in a transparent way? How do you generate more data? How do you transfer from high resource to low resource settings? And how can you quantify and better understand the process? So oftentimes in any problem, you have to zoom into these principles and understand which challenges you're trying to tackle. And for the last about 30 minutes, we'll cover why is multimodal difficult? What is new in multimodal learning? What are the new challenges and new advances in this space? So I'll broadly cover 3 parts. I'll cover recent work in multimodal foundation models and pre-training. We'll cover, in addition to that, so we'll also look at how we can adapt language-only models into multimodal versions. That usually makes it much more efficient and much more simple to get multimodal behavior. And finally, while a lot of systems allow you to generate text, we'll also cover some systems that can generate text and also generate more multimodal data. So of course, we've seen all, can we check if the audio is working? How to get the audio? It's gonna be a lot of work.
No,
Okay.
if you unshare and then reshare.
Oh, unshare and reshare?
Yeah, if you stop.
I can just voice it out, it's fine.
Okay, sure.
Yeah. So as a quick motivating example, I'm gonna play this video clip and I'll just voice it over. Oh, it's playing from a computer. Okay, people should hear it.
It's just a privilege to watch your mind at work.
Okay, so Sheldon's like, it's just a privilege to watch your mind at work. And people can recognize that this is from the Big Bang Theory. For people who have context, Sheldon is clearly being sarcastic to his friend Leonard by saying it's a privilege, with emphasis on privilege and his head shaking and his eyes rolling. Classic example of synergy, right, where it's clearly not a privilege, it seems like a positive sentence, but the way that Sheldon is saying it in these nonverbal expressions allows you to indicate that he's actually being sarcastic. So our LLMs can, of course, respond pretty fluently to almost any question you ask them. How can we build large multimodal models? So let's say you want to give this video to a large multimodal model. What are some of the capabilities you'd like to see? You'd like to see, well, several things. You might want to ask the model to classify. What is the tone of the man in the gray shirt? You want the model to be able to identify that the person is being sarcastic and obnoxious to his friend. You might ask them more open-ended questions, like describe the relationship between these two people. You want the model to identify that they are friends who are joking around with each other. You might want to ask the model to explain why by citing both visual and verbal evidence, perhaps even pointing to previous episodes and looking online to tell you that this is Big Bang Theory if you haven't seen it. You might also want the model to animate a short story inspired by this initial video clip. Imagine if a AI model could automatically fill in the rest of this scene. And you might also want to ask counterfactual questions to this model. Right? Imagine one of these people were from a different society or culture. Would that still be seen as humorous, or might this be seen as offensive in different cultures? So these are the type of problems that are, 1, 2, and 3 are, probably within the capabilities of today's models, classifying, holding a dialogue about this video, explaining. But of course, 4 and 5, and also partly 3, 4, and 5 are still big challenges that will be tackled in the next couple of years. So this is kind of where we are at now. And I'm going to cover, using this as, again, a rolling example, what really goes into making large multimodal models that can understand these videos and answer these questions conditioned on these videos. So as I mentioned, 3 parts. And the first part, we're going to cover how we can use foundation models to learn representations of different data modalities. And we'll primarily focus on text, video, and audio, but we'll also show that this really generalizes to almost any form of sequential data. So how do you take in data modalities that are, maybe different words a person is saying with different facial expressions, different vocal gestures, and learn these multimodal representations that summarize the information, their alignment, and the ways that they interact with each other. In part 2, we'll look at how we can adapt large language models. So LLMs only understand text. How do you quickly adapt LLMs to also take in the multimodal representations learned from these videos? They need to be able to take in those representations to actually answer questions based on it. And in part 3, we'll show how we can enable generation of both text, so answer responses to questions, that's in text, but how can you also generate more images and maybe generate more data? So once you have all these 3 parts, you have basically true multimodal input coming in and multimodal output coming out, right? That's, in my opinion, truly general multimodal input, multimodal output is key to AGI. All right, so let's go step by step. Firstly, large multimodal models. So the challenge here is, how do you learn representations from different modalities? And in particular, how do you learn these temporal representations of people speaking and showing gestures and having voice? And you can think about applications to your own domain as well. And of course, it's no surprise that nowadays transformers, especially self-attention, has emerged as a very viable opportunity to learn these temporal representations from different data modalities. And of course, a recap, we've seen this. Transformers are particularly useful for language. There was a recent, craze on these attention-based models that dynamically assign weights to how different words in your sentence contribute to predicting next words or predicting some label that you're trying to predict from this sentence. So again, just a quick recap. This is the key equation that we saw, that given some data X, you're going to pass them through learnable transformation WQ for the query and WK for the key. And I like to think about things from a dimensional perspective. Over here, I'm just saying if there's 3 words, then X by WQ, it's 3 by D, 3 words by their dimensions that you've learned. And on the other side, you have the transposed version of that. That is D by 3, the number of dimensions by those 3 words. And of course, this allows you to learn this 3 by 3 weighted outer product that essentially tells you how each of the 3 words, like fox jumped over and fox jumped over, how each of the 3 words relates with the other 3 words in the same sentence. Some of them relates really largely, and there's a big attention score. some of them barely interact with each other and there's no attention score. There's some normalization factors, again, normalizing by your dimension to make sure it doesn't blow up in magnitude by the dimensions of your features, and softmax to make sure each row is normalized to 0 and 1. And these are really powerful models by essentially saying, I'm going to look at how each of the words are contextualized using my attention scores with the other words in the sequence. I can use that to learn better word representations that enable me to predict the next words in my sequence, right? Lazy dog. And of course, nothing here is specific to language. The only kind of assumption that we made here is that your data is sequential in nature and can be broken down into discrete buckets, right? Discrete tokens that interact with each other. And your goal is to find all these pairwise, in this case, 3x3 interactions. So this works perfectly for vision as well. In vision, you can take a large image and you can essentially break this large image down into individual patches, right? Different patches within the image. And what goes on into most of these image processing models is exactly learning how one part of the image relates with one other part of the image. For example, that there's a head of a fox over there that relates to the tail of a fox to get this concept of a fox. The fact that the fox is something above the dog. So that shows this relationship above. So again, we can use transformers directly for these computer vision problems, where the equation basically looks exactly the same, where you take in an image, you break it down into individual patches, and what you're trying to learn using these attention scores is how each of the features for your image patches relate with other features of other image patches. So something like this. And therefore, your final output Y will be a weighted sum of your attention scores that were used to take a multiplicative sum of each of the features of individual image patches. So here is it in animation style. Take an image, break it down into individual parts. You take a linear projection and you add a positional embedding. And that together goes into a transformer encoder, which learns the pairwise relationships between the features and the positional encodings. So that's the positional encodings. It goes to a transformer encoder, and that outputs some feature which you can use through MLP to predict your labels. Right? So taking your data, they find that flattening it is often very useful. And they find through hyperparameter tuning that about 16 by 16 pixels is the right optimal size of each image patch, 16 by 16. You're going to take that into a linear sequence after you flatten it out. Over here, 0 through 9 are your position embeddings. So implicitly just assigning a label 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. People have also kind of shown that sometimes 2D positional embeddings can work better than 1D positional embeddings, just because images are 2D in nature. So instead of just doing 0 through 9, you can also do 0, 0, 0, 1, 1, 0, 1, 1, and so on. And once you have these position embeddings with each of the patch features, put them through an encoder that learns the pairwise attention between them, takes a weighted average, and outputs those features through an MLP to predict your label. So that's vision transformers. Very powerful and have been used widely throughout many computer vision problems. So one key innovation that came at around a similar time of vision transformers was that in addition to doing this for supervised learning, to have a softmax over your classes, is how to do self-supervised learning with these vision transformers. So that's there's a paper called Masked Autoencoder, where you can take in an image and you can essentially, in an unsupervised manner, black out different patches in the image. So these are being blanked out also in 16 by 16 regions. And you're going to retake whatever is remaining after randomly blacking out certain parts of the image, put them through encoder, which is a vision transformer, as again, a linearized sequence of the patches, and use that to decode what were the parts that were originally masked out, right? So again, a transformer decoder does that. So you're going to take some things, mask it out, put it through a transformer, and try to recreate what was originally masked out. And this, of course, can be scaled up because all you need here is just unlabeled images. You can programmatically mask things out and you can reconstruct them. You don't need labeled data, and therefore this really scales to large unsupervised learning. And yeah, so the target is a reconstruction loss function over the entire image. And people found this work really well. Of course, one of the key hyperparameters was how much you mask out. People found that about 70% masking ratio works really well for this setting, and about 85% masking ratio works really well for fine-tuning. And in fact, you can show that once the model is trained, the model actually does impute the masked out regions by generating pretty photorealistic pixels in place of them. So that's transformers applied to vision, right? Putting images into patches, putting that into a sequence of image patch regions with position embeddings into transformer that learns these pairwise attention scores. And of course, now that we've seen these transformers working for language as a sequence and visual as a sequence, it becomes very natural to apply them to multimodal settings. That's what we did in 2018, 2019. We developed multimodal transformers, where the idea is again very similar. We take in some language, so that's some words a person might be saying. So over here, maybe 3 words: privilege to watch your mind at work. You take in some non-verbal expressions, so the person's face and voice. So maybe they might be showing some loud voice at some point. They might be rolling their eyes in vision at some point. And that might be a completely different sequence length. It might be D by 4, right? So the first one is 3 by D, the second one is D by 4. They might say multiple different words from the number of expressions that they show. And the only key thing is that the dimensions of these 2 different multimodal features has to be the same. They have to be projected into the same D-dimensional space. And that allows you to learn a 3 by 4, no longer 3 by 3. So now it's 3 by 4. And this is again a weighted outer product. It tells you how each of your words interacts with each of the nonverbal expressions. So that's a 3 by 4 matrix. And you're going to do the same normalization by D and your softmax across your rows to learn these attention scores. Now you want to interpret these attention scores in a pretty similar way. It's just saying how each of your words relates with your nonverbal expressions. Right, so privilege might interact 0.7 with vocal emphasis and 0.3 with eye rolling, and the word mind might be contextualized fully with this vocal emphasis. And that can be used to take a multiplication with your actual nonverbal behaviors, which is 4 by D. If the dimensions all match up, you get a 3 by D output. Right, so this 3 by D output is essentially telling you a new representation for each of the words. So the word privilege, but now it's taken an attention weight over your 4 nonverbals and multiplied by those 4 nonverbal behaviors to get a new representation for the word privilege after looking at the nonverbal expressions of the person. So we call that a new language representation contextualized with vision. And now these are much more powerful, whereas the previous representations of privilege and mind, you might just think the person is being happy and positive because privilege is a positive word. Now these language representations contextualized with your vision actually allows you to predict that the person is being sarcastic. Great. So multimodal transformers have been used extensively. Over there, we show these cross-attention transformers. So language is being enriched by vision. And of course, in most settings, you would do both directions. You would do language being contextualized with vision, and you also do vision being contextualized with language. So bidirectional. And then you would pass it through some more transformer models to make a prediction on the label. And in fact, you can actually find that most of these cross-modal attention scores, so how your language words interact with your vision words, vision pixels, are actually very intuitive. So these are folks who trained it on lots of images and captions. They scaled this model up. So you can look at the attention scores for your caption. For flowers, it actually does learn this attention matrix of pixel regions that show the flowers. For wall, it shows the pixel regions of the wall. For cloudy, it shows the pixel regions of the clouds with the highest attention. So pretty intuitive outputs of these cross-modal attention matrices. So nowadays, these multimodal transformers are used virtually everywhere. They're used in vision language pre-training, lots of unlabeled data. You can apply multimodal transformers and make self-supervised predictions. And you can put a language model decoder on top of that, and this gives you a lot of these multimodal language models. I also want to highlight the work that some of my colleagues did in applying some of these multimodal transformers to biology and medical data. So you can take all these cellular data, again, these are really high resolution. Under the microscope, 70,000 by 87,000 pixels. That's beyond the scope of what any convolutional model can take in. So it makes a lot of sense to break that down into 256 by 256 image patches. So you patch from the top left, go row by row and patchify that image. That gives you a sequence of smaller image patches that are within a scope of today's vision models. And you can also take in a sequence of genome expressions that were sequenced from these cells in the image. And we applied multimodal transformers to these across the different image patches and across the different genome expressions, both of which are sequences, and use that to predict the risk. So what kind of cancers and what kind of risks these patients might pass away from these cancers. And again, these attention scores are quite interpretable. You can see that it's first picks out genomes, this EMT genome, can't really pronounce it, but EMT genome is very indicative of cancerous growth in cells. And at the same time, it's highlighted in red, high attention scores to tumor cells that are invading nearby healthy cells. So it's learned that relationship between the genomes and the images. Okay, several last things about multimodal transformers. We've mostly been looking at settings where data modalities are pretty much discrete, like words with nice boundaries, images with nice patches. There's of course settings where data is much more continuous and it's not very clear how to break them down into individual boundaries. So speech is one example, right? Speech is very continuous. So one key idea was to, in these folks, they call hidden unit BERT, was essentially to take your continuous signals and first do clustering so that you can convert that into discrete clusters. And you can do something like k-means clustering of each of these continuous signals. So once you've done k-means clustering, you can say essentially transform those continuous data into discrete one of three clusters, 1, 2, 3, and then you can put them through a transformer, learn representations, mask out certain regions, and then use the features to reconstruct the missing regions. But now the reconstruction is essentially classifying which of the three clusters those missing speech regions belong to. So classification is always easier as a training objective than regression. So transformers, and especially multimodal transformers, can also be extended to continuous modalities. And based on all of that work, we also develop what we call high modality multimodal transformers, essentially multimodal transformers for everything. So you see all these different data sets that you have. Sometimes you see language, speech, and gestures when trying to understand a person. Sometimes you see image and text from the internet. When you're dealing with robotics, it's mostly force and proprioception data, both sensor sequences. Medical is mostly tabular and sensors and so on. Basically, the whole world can be seen as a partially observed multimodal problem, where different data sets are just different subsets of the input data modalities and different subsets of output tasks. So training one general model can be very useful because it can generalize to what is low resource, and it can also enable you to share information across different inputs and outputs. So we did exactly this. All of these data modalities can essentially be standardized into a sequence, language through a sequence of words, speech through a sequence of time steps, images through the sequence of patches, and so on. You can apply modality-specific embeddings for each data modality. You can train one shared unimodal transformer, so that learns the relationships within each modality. You can have a shared multimodal transformer that learns the relationships between one modality and another one, and do multitask training to predict different tasks. And this actually works. You can train one model architecture with one set of parameters to do many different tasks with many different inputs and outputs at the same time. So it can do things like, tackle these like videos, right?
It's just a privilege to watch your mind at work.
Predict sarcasm and humor and emotion from videos of people. It can understand images and text, all your multimedia data. We've applied them to physical sensing data. These are IMUs and tactile sensing, pressure sensing, based on what people are wearing, like shoes and gloves. And we also applied them to robotics data, again, tactile and computer vision problems. So Also, of course, big opportunity in applying some of these models to various forms of scientific data, whether that's a sensor or a sequence or satellite image and so on. Okay, moving on, I'm going to quickly cover, so that was all about learning multimodal representations. How do you take in lots of data, mostly in some sequential form, learn the alignment and interactions between them to learn very powerful representations. Now I'll cover how to adapt large language models to take in these representations and actually allow you to do question answering on these representations. So a key idea that I'll cover is what we call adapters. Adapters are essentially taking these large language models and you want to freeze them because most of these large language models are huge. You can't really afford to train them on your own computers. But if you freeze them, they only ever understand text. How do you get them to understand some other data modality? So what these adapters are essentially nice, very small prefixes, right? So you can take in an image, you can define some CNN or vision transformer over the image to get some features, and this adapter essentially takes in these visual features and brings them into the input space, the same dimension of these LLMs, right? So the adapter will be prefixed and prepended in front of the LLMs, and that gives you an adapted plus pre-trained model, right? One that first takes in the adapted features from vision into the token input space, and then takes in the words through the frozen LLM. So this is called prefix tuning. It works for text. You can add, previous text instructions, but it also works for other modalities like images and so on. So to see examples of this, you can take in this image, pass it through a model, adapt it as input, add your question, what color is the car? And now all those are put as input into this frozen LLM that can then output blue. You can, so this is purely zero shot, right? Purely zero shot, doesn't need any examples. If you feel your model can't do it from purely zero shot, you can also give it one example. So you might give it an image and ask the question, who invented this? And give the answer, the Wright brothers. So the first part goes adapted into the LLM. The second part just directly goes into the frozen LLM. And you can then give it your actual question. So a new image and the question that you want to ask, who invented this? With the answer, and the model would correctly output Steve Jobs. So the model can do some very cool things by just using these adapted encoders before the LLM. So people have really scaled this up. Flamingo and some of these early multimodal dialogue models do something like this. So you can have multiple rounds of question answering with these images, as long as the language models take in the adapted features as an input before doing a dialogue. Mini GPT-4 is also a resource I like very much. It's it tries to be a replication of GPT-4. And what it does is that it takes the best frozen language model, which back then was Vicuna, so something that was instruction tuned, so really follows people's instructions. It takes in some image, passes it through a frozen vision transformer and Q-former. So these are just ways of representing images. And again, it's frozen. And all it does is that it trains a linear transformation from the output of your vision model into the input of your language model, right? So this linear layer can be very small, right? This output might be 1,000 dimensions. This input might be 768 dimensions. This is just a 1,000 by 768 matrix. So now you can essentially train this model through two stages. First, alignment using paired image and text data. You will give it some images and try to let the model caption the image. So that learns the alignment between image features and language model outputs. And that's used to train this linear layer. So that's a captioning step. And then you would do instruction tuning. So now instruction tuning, because we don't want to use these models to just always caption our images. We also want it to do some other cool things. So you might want to ask, what do you think of this logo design? And you want to give some human annotations of what human experts would answer these questions. So that's what we call instruction tuning. Taking in the image, taking in the instruction, and trying to get the model to predict what the humans would predict as the answer to that question. So that's Mini GPT-4. Another cool resource I like very much is called Llama Adapter. Llama, as all of you may know, is the open source LLM series from Meta. Probably the most open source sets of models we have. And Llama Adapter basically trains a large set of adapters customized for this Llama model. So these adapters can be taking in 3D point clouds, through some representation and adapting that into the input of the LLM. It can be also taking in different languages, like in this case Chinese, and adapting that into the LLM. So that allows you to do very cool things like taking this 3D point cloud, give it a task of generating the image from this 3D point cloud, and it can generate the answer. And you can also do it for different languages. Okay, I mean, a quick note about these large data sets. Of course, there's lots of large multimodal pre-training data sets to pre-train your models, and they've gotten larger across time, also become much more public across time. Nowadays, mostly 12 billion, 6.6 trillion tokens of text. And that's to pre-train your models, but also lots of public multimodal instruction tuning data sets. These are to fine-tune your model to complete tasks that you want them to complete. These are more scattered, might be smaller in nature and more specialized. Maybe there's a medical instruction tuning data sets for medical modalities. There might be one for science, for satellite images, some for some other tasks and so on. Okay, for this very last part, so we've seen taking in multimodal sequences, learning representations, and then we saw how we can adapt them into LLMs so that they can generate text and answers to questions conditioned on these representations. And to finally close the gap, we're also going to cover some work in generating multimodal data in addition to generating text. So now you have real multimodal input, multimodal output. So this is essentially a translation problem. How do you take a text or semantically represented in text and generate images? And of course, we've seen lots of cool progress in essentially training these text-to-image diffusion models based on this principle of text-to-image generation. So how do these work? At a very high level, I'm going to cover several key things that makes it work, especially the multimodal components. And in most of these models, there's three components, right? There's images that come in, and usually these images are encoded into some feature space using something like CLIP. And I'll cover very quickly what CLIP is, but you can think of CLIP as a way of representing images in a very nice manner while maintaining some similarity with text. So it's not an image-only representation, it is an image-text coordinated representation, and we'll see that very quickly. Once you have image representations, how do you take in text, learn some features, and use those features to predict the image, right? That's learning the mapping between text and the image features. And once you've learned this mapping, how do you take these image features and, of course, reconstruct actual pixel level images? So that's the generation part. And of course, nowadays, diffusion models, we've seen whole lectures on diffusion models and how do you take features and generate high resolution photorealistic images. So each of these one by one. CLIP, as we mentioned, is a very popular encoder for image and text, especially if you're dealing with multimodal problems where you want to bring image and text very close together. And this really falls into this representation coordination sub-challenge that we discussed. How these models essentially work is that you take in language, pass them through an encoder, you get feature ZL, image, pass them through an encoder, you get feature ZV, and your goal is to really have separate representations that are coordinated through some function. So this coordination function can be something like cosine similarity, and you essentially train this model by taking a bunch of positive pairs, so image and text that are talking about the same thing. Those are called positive pairs, and also image and text that are talking about different things. Those are what we call negative pairs. So if you take in a batch, everything on a diagonal, if you compute a matrix similarity, everything on a diagonal would be the entries with the positive pairs with the other data modality, and everything off diagonal would be negative pairs, right? And these models are trained with a contrastive loss that essentially tries to maximize the similarity of positive pairs, where similarity is something like dot product cosine similarity, and you're trying to minimize the similarity of negative pairs. And these methods work really well. They're great encoders for language vision tasks. They keep separate coordinated representations that are not identical, but allows you to do some form of similarity search based on what is nearby. So this allows you to do things like zero-shot prediction. You can take in an image, you can give it a bunch of captions that you want, and it scores which of the captions is the closest in describing the image, right? So you can take in, for example, over here, it takes an image, and you can give a bunch of captions, and it rightly recognizes is guacamole, right? We call this kind of zero shot or open set prediction because you're no longer limited to 4 or 5 image categories that were predefined in your training data. Now you can give it any set of categories and see what's the right one. Some of these models go through CLIP, and of course, CLIP is very useful because CLIP can essentially allow you to do retrieval. So you can take some of these models that take an image and captions, and you can train them to generate more captions while also taking the captions that a model generates and using this clip-like loss to generate, to retrieve the nearest image that is representative of those captions. So again, over here, the model might generate a silhouette of a plane against the sunset as the next caption. And it can actually generate the input image out of a set of images that most closely represents the silhouette of a plane against the sunset. So that's one step in enabling these forms of multimodal dialogue models. So for example, here's an example. I'm thinking of an animal. It is brown and furry and has a tail. What is it? The model says a squirrel. You say, no, the animal I'm thinking of lives in the river. The model says a beaver. And you say, that's right. What do beavers look like? The model says they have a tail. And you might say, show me an illustration of a beaver. And given those contexts, the model can take in that representation and essentially retrieve using clip-like losses the image of a beaver. You might say, what about a pencil drawing of one? You can generate a pencil drawing. Or what about a photo of one? You can generate a photo. So lots of cool examples. By having this clip-like loss on the output, it can enable the model to both generate text and generate images through retrieval. Of course, not always do we want to do retrieval. Sometimes we also want the model to do some generation. So nowadays, we also have models that are connected to generative models on the output side so that the model can generate text and also fully generate pixel by pixel these images. So here's an example. Again, these are based on adapter models. So you have, how should I display these at the farmer's market? That's your task. Through a tokenizer into the LLM, you give an image of the cookies that you just baked. That goes through a visual encoder and a linear mapping. These are the encoders that we talked about as a prefix to the model. That together goes to an LLM and it generates the output of the model. I think we should put it like this. And the model can then decide whether to retrieve some candidates of how it should visualize it, or also generate using stable diffusion what kind of outputs it would like to generate. And it can essentially give you, both of them. And you can also choose based on what the user prefers. I think I look best when they're on a tray, a little bit of space, and therefore return you the generated image. So that's really enabled a whole generation of models nowadays that can essentially do multimodal inputs and multimodal outputs, right? You can give it image and text, and the model can learn representations to understand them, and the model can also generate text and generate images to correspond and to hold dialogue with you. So lots of more examples over here. Okay, so to summarize, we saw a high-level introduction to multimodal AI across 3 main stages, right? Firstly, what is multimodal? Multimodal, it is the scientific study of heterogeneous. So that refers to data modalities that are very different from each other with different properties, and which makes them very difficult to process in a single model. At the same time, these data modalities show some connections, right? There's some overlap in information between them. And finally, they interact in some new way to bring about some new information for your task. So those are called interactions. Why is it hard? Because of these 3 principles. There are new challenges that arise in multimodal learning in representing the elements in your data modalities, aligning multiple elements, especially those in a sequence, reasoning to make compositions and to make good predictions, generating more data, transferring from high resource to low resource modalities, and quantifying deeper empirical and theoretical understanding of these models. And of course, we saw what is next. Lots of interesting work in multimodal LLMs, starting from language-only models and making them multimodal, building systems that can also generate multimodal outputs so that they can interact multimodally with people, generative AI, and all sorts of applications in physical sensing, understanding health and well-being, and developing autonomous multimodal agents. All right, so that's all, folks. Happy to take any questions in the remaining time. Thanks, everyone.
A quick question about the multimodality LLM, especially your example with the big bang theory. So at the beginning, you mentioned that multimodality includes audio, text, and video. But in your explanation, it seems that for the audio, you only use that audio extract the transcript from it. And later, when you are fitting into the model, you only use the text and the video. So that means the audio is kind of like nothing.
Not necessarily. So in this case, vocal emphasis is a feature, right? So you can put in audio through things like MFCCs to extract amplitudes and variations in voice in the frequency components, and you can recognize that high frequencies might be interpreted as a louder voice with more emphasis. So those could also be raw features. Right? Yeah. Yeah, great question about the position embedding. So over here, we have data that is time aligned, right? So I know that I said the word privilege at this time, and I had the vocal emphasis at the same point, but I had eye rolling, 5 seconds later. So that information actually does go into the position encodings. Of course, you might also have settings where you have satellite images across a month and you have sensor readings across every day. So it's not very time aligned, and maybe there's the position embeddings could help you synchronize those two sources of data, which is collected at different resolutions. Mhm.
But I guess could also do the opposite, right? Could also get a continuous embedding of text and work with other.
Of course, yeah.
Why is everybody sort of set the sequential data?
Yeah, I would say 80–90% of people are working on transformers now. Naturally, very scalable, lots of resources to support it, but there's also nice alternatives to transformers, which are more suitable for continuous data. So things like state space models, diffusion LLMs are coming up as, that 10–20%, but they're slowly rising. But I've seen a lot of people, if they're dealing with things like sensor data, they might prefer to use state space models and everything becomes in continuous domain, or they might use diffusion models, right? So it's all reasonable. You still have to decide though, is it the goal of bringing everything into discrete space or bringing everything into continuous space? Because if you have hybrid models that have both discrete and continuous inputs, I'm not seeing really cases where that works well. Yeah. Sure. Embeddings. Yeah. So those would not be interpretable. This would just be embeddings. And oftentimes, the only restriction on the linear layer is that it matches the input dimension of what goes into the LLM, right? As long as it's like 768 dimension, then it's fine. Yeah. Surprisingly, linear layer works. I mean, it depends on the setting, right? Here, you clearly have settings where the text and image are very well aligned, right? They have almost exact semantic information. It's kind of a setting where imagine if two data modalities is Venn diagrams and they're almost perfectly overlapping, and linear mapping seems to work. I don't know how this will generalize, and maybe people have tried it, but I don't know how it will generalize to things where the overlap between data modalities is not super clear. Maybe linear layers have to be expanded to more expressive transformations between them. But yeah, as of now, it pretty much seems to work. Yeah.
the sensor differing like significant like the difference. For example, when we collect XCT, we have like images in like DL space, and we have like exciting images, which we extract information from the real reciprocals. Do you think this kind of framework is that?
Yes. I mean, we can talk more, to know more about a problem, but yes, I've seen like many examples of AI. I mean, I work with a lot of people in manufacturing, so we apply some of these systems to various sensory data, and sometimes the question is about just making better predictions and doing multi-sensor fusion. Sometimes the question is about having language as a way of kind of, explaining things to people, doing training of people, training of new workers. So lots of opportunities, I think. Yeah. Yeah, you had a question?
Need like your kind of structure, like it's not like please describe this image in various ways of saying that. There can go back component out
This one?
there are some models on the that have it up, but like so like okay, test question. Please describe this image. Some version of that phrase. That's what it's like. But I think it like if you train data like that, like you have to up.
Yeah. So I feel, I mean, there's two differences. One is like kind of what goes into the system prompt and what goes into the user-facing prompt, right? I think there's lots of methods nowadays where, like, text and image and all those like semicolons, all that system prompt is abstracted away. So nowadays you can pretty much just say, show me a photo or generate me a photo, and the model does something internally to do the retrieval, but it just outputs something at a pretty high level, user-friendly level to you. Yeah. Yes.
When we try to combine the information like a film image or text or vectors, they have different shapes, right? So we have different values. If we do the fusion of the information, we have to keep them that shape.
Sometimes, not always. Yeah, so I mean, it really depends, right? I think, sometimes when you do like contrastive learning, then you got to bring them into the same embedding space to measure the similarity. For transformers, you got to measure the attention scores using the same dimension. But for like these different things like fusion, you can do different attention weights. You can build different multimodal interactions, and yeah, it really depends on the method. They don't necessarily have to be the same shape. There's also settings where you can do fusion of tabular with time series. So one is a sequence and one is just a table of entries. So one not sequential, and it really depends on the problem. But the survey paper that we have categorizes and outlines, all the settings, right? Static and static fusion, static and temporal fusion, temporal and temporal, and summarizes different methods. Yeah. Great. Any more questions, folks? Yes.
Perfect. Okay, that concludes the day today. See you all tomorrow morning for a tutorial session.
Yeah, just a reminder, the special button